How's everybody doing? How did you think the homework went this time? Pretty good. Everybody feels more confident about partial derivatives and total derivatives than before, even though we'll have a lot more practice coming. So I guess I was thinking about it's easy when we get down into the weeds of things to forget the scope of where we're going. We're building up, so that we're ready to talk about differential equations, sort of after the midterm. Right now we're kind of headed there getting all the pieces in place. So we have linear algebra in place, we're gonna need that. We've got vectors, a little bit of vectors, we're gonna have some more vector pieces in place. We're gonna start talking about integrals and today, but we also have multivariate derivatives. So we're gonna be comfortable jumping back and forth between the integral and the derivative forms. So the fundamental theorem of calculus that we had, I'm going to start there. So what does it mean that the derivative and the integral are inverses of each other? Or does it mean anything? Yes?
Like it's that putting them as a composite function will return the argument.
Yeah, exactly. So sometimes it's written like, if this is true, if that's the relationship between little f and big F, then this is this, right? So this is sometimes, so this is a constant, this is the value x, that's the value here. T is the dummy variable in this version. It goes away when we do the integral. So some of the key pieces of this that are maybe not, boy, let me slow down. On the big picture, this is one version of the fundamental theorem of calculus, but it's actually not enough machinery to do what we need to do when we get to partial differential equations. We actually need the multivariate versions of this formula. And the multivariate version is going to be things like the volume integral of a divergence is equal to the surface integral of flux through the edges of the volume. There's a similar one for the curl. There's a similar one for the gradient that looks an awful lot like this, except it's following a particular path in higher dimensional space. And we need those. Those are going to be the fuel that we're going to use to build continuum mechanics and PDEs. Those are the essential elements of how tensor analysis works. So this concept that we have integrals and derivatives and we're jumping back and forth, we want to be really down on taking partial derivatives because those objects will be built on partial derivatives, and we need to be really down with multivariate integration because that's the inverse of a combination of partial derivatives. Special combinations of partial derivatives, not all of them, just a few that are the most important ones for the physical reality that we live in. Does that make sense? We can live in a different physical reality. So the problem with learning this in the math department is that they tell you, this is just one set of this whole general notion of integration and differentiation, and then you get totally confused and you're like, well, wait, which one is the one that's the correct one for the reality that I live in? That's the one we're going to be focusing on, but we actually need more tools than you tend to get, specific tools along those lines, because those will be the ones that will be our building blocks for our physical theories, the physical theories that look like our world. So that's where we're trying to go. Okay, so does that make sense to everybody? I realized we hadn't talked about where we're going. So we have these two chapters. We're going to do chapter 6, which is on integration, multivariate integration, and then chapter 7, which is getting a little deeper on Fourier transforms. And then we start to pull all those pieces together before the midterm in chapter 8. And then after chapter 8, we're going to be just talking differential equations. So after the midterm, it's differential equations for the rest of the semester of different flavors, different types, sometimes ordinary, sometimes partial, sometimes nonlinear, sometimes linear. And you'll see that all these tools we've been building on up to the midterm will all be coming back to drive our discussion of those kinds of systems. And then the end, we'll end up being able to talk about fluid mechanics and solid mechanics in a deep way with all the tools coming together to feed into those equations. Okay? All right. So, let's look at this a little bit more carefully before we jump into the multivariate version. Where does the t go in this? Okay, when I take the integral, does the answer still depend on t? Doesn't. If I didn't write these, would the answer depend on t? Yeah. So that's sort of conventional that you would keep the t and then you put these in and then it doesn't depend on t. But how do you think, what is an integral anyway? Like how do you think about it like mechanically? What are you doing when you're taking an integral? If I make a plot for you, whatever, that's my function. What's the integral? The area under the curve. So first of all, you have to be careful that 0 is actually on there, because if you do it from, you need to go all the way to the bottom. And so frequently people think about taking the area under the curve by breaking this up into little rectangles that are kind of tracking the function as you go. I'm not drawing it very well, but something like this. So this is called Riemann integration after Riemann, the mathematician. And so what do you do with all those little rectangles to get this integral? And where on this integral also would be x and a? Where should I draw x and a on this figure?
X is on one side, A is on the other.
Something like that. Okay? So, what do I do with all these little rectangles?
Sum them.
Sum them up. So this thing, really, we're going to say it's approximately equal to a sum over all the little rectangles. And how big is the rectangle? So it has a width, dt, and it has a height, which is the function of t, and we have a mess of them, because we have so we sum over, I goes from the one that's at a to the one that's at x. So, does that make sense? So I was the, whatever I it is that's the one over here, to whatever I it is that's the one over there. Does that make sense? Okay. So where does the t go then? In this form. This still looks like it's a function of t, but is it? Like if you really think about doing that sum, what are you sticking in there?
You're evaluating the function at a bunch of different t's, and then once you've done that evaluation,
Exactly. So this is really, so Jean just put it very nicely. When I go through this, dt is just going to be a number, so whatever it is, 0.1. That'll be 0.1, and then let's suppose that the function is 93 right there. So each one of those would be 0.1 times 93. It doesn't depend on, and there's going to be a whole mess of plots for all the different i's you have to sum up. So each one of them no longer depends on t because you've actually plugged in for the value. So when you look at this formula and you see these things inside the integral, you should have that in your mind. The t is gone when I do this because I've plugged in for the value and then I've summed up over them. But these funny ones are still left because there's a whole mess of other little boxes that I could have chosen to go on to whatever the function's doing. We're supposed to think of the ones out here as being, after I've identified all these little sums, what are the limits on this sum? So then I could go in and do that. But I could change those after the fact, and all I'd be changing is which one of these, what set of those rectangles I'm including in my set. Okay? Everybody understand what I'm going at? All right. So now, when we go to write a multivariate form, we're going to see that the limits on the integration are way more important, because the limits on the integration are going to be part of the story on the next integral in the enclosed set. So the first example I did, according to that, in the opposite order, so try to stick in the same order. Y, the X, the Y. Okay. So how do I now got a function that depends on two independent coordinates? And I've written it in such a way so that you can, in your mind, put a little bracket around the first one. So when I do this first integral, what happens to the X and Y? The X goes away because I do this sum, but instead of these being numbers, each one of them is still a function of Y. So it's not a number, they're still functions of Y. All the little functions I'm adding together are going to be functions of Y. But they're not going to be functions of X anymore. The X part has been taken care of in this integral. And then these two I've written them as constants, 0, Lx. So when I plug in the intervals on the ends, the X is totally gone. So now whatever this is, let's write it as capital Z, it's going to be a function of what? Or just this part?
Just Y.
Just a function of Y. And it might also depend on Lx, but it's not as a variable. And then if I do this integral, what happens to the Y? Y is gone, and now we're going to have super Z. It's a function of Lx and Ly, but not X's and Y's. Okay, so let's do the not exactly trivial example where Z equals 1. Okay, what's the first integral with respect to X?
X.
So it's equal to X, and then I have to do what? I have to evaluate it. So it equals X, which I evaluate at Lx, and 0, dy, which is 0 to Ly of Lx minus 0, dy. Now what? Okay, so I do the first one, I get an X, but then the X is gone when I plug in for my limits. Right? So now what's this one? The 0 is gone, but how do I integrate Lx with respect to y?
LXY.
Yeah. It's not supposed to be tricky, but it's still. And then I don't have the integral anymore, but what do I have? I have to evaluate it at Ly, 0, and I find Lx times Ly is my answer. What physical problem have I just done? Let's think of a picture. was drawing something, and I had an x-axis, and I had a y-axis, and I had LX, and I had LY, and I had zeros, and I just integrated the function 1 over that area. So what did I do?
Because it looks like it's a volume of this rectangular prism 1 unit line.
Yeah, so it's the area. It's the volume in two-dimensional space. So I just found how big it was. And that was because I was integrating with 1, so I just said, let every unit of length function as a unit of length. And I integrated in the x direction, I integrated in the y direction, I found the area of that circle square. What if instead I wanted to integrate the circle who sits between Lx and Ly, not the square? What would be different? Would anything be different in this integrand? The 1, it would still be a 1, I still want area, and there would still be an x integration and a y integration, so what's different? The bounds have to be different. And they have to be different in a special way. Because when I integrate from 0 to Lx on x, I need to have the bounds still know about the limits in y. So I'm integrating this way, but I have to, for each x, I have different limits depending on what y I'm sitting in. So I have to figure out how to do that. Does that make sense? So because if I'm at this y, I have just this chord that I'm trying to evaluate, whereas at this y, right in the middle, I actually have the full thing that I had before. Everybody on board with this? Okay, so I'm going to erase our very elaborate reconstruction of the area of a rectangle. Okay. So, for a given y, what's this point and what's this point? What's a function that prescribes that circle?
Just like x squared plus y squared equals 0.
Yeah, so it's some funny. I know that there's like an r squared, and it's equal to x squared plus y squared, but it's not actually that x. It's the x that's offset from Lx over 2, and the y is offset from Ly over 2. Does that look like the thing? And then I actually know what r is, because I know how big it is. How big is it? How big is r? And actually, is it always a circle?
0.5? 0.5?
It's 0.5 in units of Lx and
oh,
Ly,
yeah.
right?
Yeah.
I'm playing a sort of fast and loose game that Lx and Ly could potentially be different, and this thing would be an ellipse. Just kind of a mess. We can make our lives a little simpler just for the purposes of this, and make Lx, suppose Lx equals Ly equals 1, just so we don't go crazy. And then this becomes a 1/2. This becomes a 1/2. This becomes a 1. Okay, so that's the function for the outer part of the circle. So now at a given y, What are those points? I need to solve this equation for x, right? So if I do that, x minus 1/2 squared equals y minus 1/2 squared minus 1. Then I take the square root. Minus. Then I take the 1/2 the other side. Okay. So I was careful when I took the square root to keep both of them. Why?
Because the formula would be on the right side.
Yeah. So I've got both of them. So I can say this one equals 1/2 plus the square root, and this one equals 1/2 minus the square root. And what does the square root depend on? It depends on y still, right? Am I gonna get into trouble if I do that? Let's think about it. Plus 1 or minus 1? Okay, so move this outside. Okay, so I do this first integral, and I can do the first part. What is that? Forgetting about the bounds. Just gonna be x, just like it was for the rectangle. But then I'm gonna plug in these limits, and then it's gonna be what? I still don't know what the limits are there. We're gonna come back to that.
The first bound minus the second bound.
I mean, the first bound minus the second bound, and those are functions of y. So when I did the rectangle case before, I got something that was a function of x, and then I plugged in Alex minus 0, and I got something that wasn't a function of y. So I didn't have a different bound depending on where I was in the second integral. So the shape of the domain of integration is coming from the fact that the first integral has that in it. So this guy is going to be equal to the integral with whatever bounds, we haven't decided yet. And so it's going to be 1/2 minus 1/2. 1/2s go away. Square root y minus 1/2 squared minus 1 minus the square root of y minus 1/2 squared minus 1 dy. Sorry, quite a bit better. Okay. So now I've already limited myself to this function. So what are the limits on the second one? What should my limits on my y integral be? Should it depend on y? No. Should it depend on x? We could play the same game in this direction. And for every x, I could tell you an upper and lower value of y. Do we want to do that? People shake their heads. Why not? Yeah.
Different thing, should the radius from what happened?
Yes. Thank you. Thank you. So why do I not want
is already captured in the bounds tool.
Yeah, and I want my answer just to be an area. Like, in fact, what is the answer I want? We know what the answer is. It's pi r squared, which in this case is pi over 4. So that's the answer. So it does not depend on x, it does not depend on y. So somehow, this crazy thing has got to take care of that. So, I claim we can just do this. We don't need to do, the information of the shape is already built into the first integral. And then if we did this, we would get back through there. So does anybody have a sense of how to do this integral? We're not going to do this integral. We're just going to take that as given. But does anybody know what would be the BC calculus thing, horrible thing that we would now do and spend the next 20 minutes on? It is a trig substitution because this thing is like beautifully a trig problem because it's got a circle in it. So of course you've got arctangents and crazy things you'd have to do to get this right. But that's the essence. Is obvious that what we're doing is we would get back to that. Now we could have done this without a trig substitution if we had chosen our axis more conveniently and we had gone into polar coordinates, which is one of the things we need to talk about is how to change the system. How would we, does the answer change if I put the coordinates in a different location? Better not. That's sort of like dimensional analysis. It doesn't matter where I decide to set my 0 with, it's the size of the circle is the size of the circle regardless of how I measure it. So that should somehow come out. And it is definitely the case that that would have been a simpler problem. Because then we could have just said x squared plus y squared equals 1/2 squared and been done, and we still would have had this funny double nested integral, but we might have been choosing to do a different double nested integral. We could have done one in polar coordinates, like going around the circle and going out in distance. Okay? So what if we had done the y integral first, instead of the x integral first? What if I decided to switch this? When we're doing normal antiderivatives without worrying about these bounds, we just switch the order of integration all the time. Like we can integrate in y first, we can integrate in x first. I could do it, except what? I mean, with a function of y, if I did it naively, I'd have to go through all this work again to think about it. And it's really similar to the Leibniz formula at the end of the partial differentiation chapter, where if the bounds depend on the function you're differentiating with respect to, you have to also differentiate the bounds as well as the thing inside the integral. This is, if I'm integrating with respect to something that the bounds depend on, I also have to worry about the integral of the bounds, not just the stuff inside. Okay? If the bounds don't depend on it, like in our rectangle problem, could we switch the order of integration from x first, y first? Totally didn't matter. We would have gotten exactly this Lx times Ly every time. So, what is it that makes this problem easier than this problem? In that sense. In the way we did.
There's no depends on the variables and the bounds.
It depends on the variable and bounds of the integral. We happen to choose a domain that was natural in our coordinate system. If we chose a coordinate system where the bounds naturally occurred, so distance from the origin, angle from the x-axis, if we went into our theta coordinate system, it would have been just as easy. We would have had a fixed area r, and theta would have gone from 0 to 2 pi, and it wouldn't have depended on which r we were at. Does everybody see how that works? So the machinery we're gonna develop in a minute for how to start thinking about how we change coordinate systems is valuable, because this is a nightmare. We don't wanna do this for problems of even remotely complicated dimensionality. We would much rather choose everything to be simple in our coordinate system. Okay? So what are some Earth-focused problems where this might be relevant? What would the natural coordinate system of this room be?
Rectangular, Cartesian.
Rectangular, Cartesian, so it might be X, Y, and Z, and maybe I put the axis over in one corner. So, you know, that's LX, that's LY, this is LZ. It's pretty, everything in this room could be simply described, and that is like a fraction of the room. But what if we're thinking about this room in the context of the Earth? Then what do we want? Sorry? Polar, yeah, so polar would be helpful because the Earth is round. So if we're sitting here in Rhode Island in our little rectangle, so what are some of the important directions?
Radial and azimuthal.
Yeah, so there'd be a radial direction. And what is the radial direction? Does anybody know? It's kind of a fun geophysics question. Does that actually point to the center of the Earth? Or to put it another way, if I take this stick and I hold it, which way does it point?
The center of gravity.
Center of gravity, plus also something else, which is the crazy part. The Earth is rotating, so there's also a centrifugal force on it due to the rotation of the Earth. So it doesn't quite point at the center of the Earth because there are two forces involved. There's the force of gravity, and then there's also the centrifugal force. So we take the combination of those two, and that's the direction of a plumb line, a pendulum hanging down. That's what its natural position is. But anyway, sort of the center of the Earth. We'll do that problem in more detail later. So if I take those two, so it's a little bit, increase that, so it goes a little bit below the center of the Earth, I guess. This is about 1/300th of that in magnitude, so it's actually not that far off, but it is still there. And so the Earth is not actually a sphere, it's an oblate spheroid. It's a little bit skinnier at the pole and a little bit fatter at the equator, like that. Not nearly that much, but that's what it is. Okay, so, and it's, you can think of it as just like, if the Earth is spinning and everything squishes to the lowest level, it's not gonna be the lowest level of gravity, it's the lowest level of the combination of the centrifugal force and gravity. And that's what it makes flat. So dirt might not be flat, but the ocean for sure would like to be flat if it wasn't moving, and it would go to that surface. Okay, so so now we have some sense that we would define that in the direction of the negative of gravity plus centrifugal. Okay? So that points in the same direction. That's a univector pointing in that direction. Okay, what else do we, so azimuthal, so which way is azimuthal? So this one has some symmetry already built into it because of the centrifugal force. How does the centrifugal force orient itself? outward from something.
So from the axis
Outward from the axis of rotation. So if we want this direction not to depend on longitude, we better define longitude relative to the axis of rotation. So, and if we do that, so that this direction is the same at every longitude, we have to do it in a coordinate system where the axis of rotation is one important direction. Okay? And so now we know what azimuthal is. It's longitude relative, not to the magnetic North Pole, but relative to the rotational North Pole. Okay? Does that make sense? Okay, so is it convenient to say that this is 6,370 kilometers and this is 6,370 kilometers plus 1 meter and this is 6,370 kilometers plus 2 meters? Not exactly. So frequently we would take that as the unit vector, but we would actually say we define a local z coordinate which is in the direction of r hat, but it's a z value that has the radius of the Earth added onto it, or subtracted off of it. R minus r radius would be the z. So that it would have, so that it would just be relative to the some local version of the radius of the Earth. Okay, so if we do that, and we define, so then we have latitude, longitude, and that z, we have a new coordinate system, an Earth coordinate system, which is convenient to use. So that's the one in the notes that I put down, and then we could talk about integrating over the volume of this box. And this box will be defined in this direction by z limits, whatever, 3 meters to 0 meters, and in this direction, because that's north, by latitude, and in this direction by longitude. And that would be a way of describing this box of Earth coordinates. Does that make sense to everybody? And that would be sort of normal. It probably isn't really north, south, east, west, but for pretend we can just say that it was. Okay, so let's talk about integrating then in coordinate systems other than Cartesian. So what if I did want to integrate that circle in its native coordinate system? How would I write the integral? I want to integrate in r and theta. So I've got a circle, I've got an x-axis, but it's sort of a pretend x-axis, and a y-axis, pretend y-axis, but what I'm really defining the coordinate system in is theta and r. So how am I going to integrate area? Well, what's my z going to be? 1, same as it always was. And then I want to integrate in theta, and then integrate in r. And what are my limits going to be on an r? 0 to 1. And what are my limits going to be in theta? 0 to 2 pi. And let's just do that integral and see what we get. Well, we do the first one, integrate 1 in r, what do we get? I get r, I plug in for r, and the limits, 1 minus 0, and I have 0 to 2 pi, d theta. What do I get? This, I get theta, and I plug in for 2 pi. Is that the right answer? What happened? Radius is 1/2. So we did something wrong. Oh, radius is 1/2. That's a good one. that was one thing we did wrong. So this should have been 1/2? Is that the right answer? Oh, it is the right answer, isn't it? It's not supposed to be the right answer. What are the units of that answer?
Isn't the right answer pi over 4?
Hmm?
Isn't the right answer pi over 4?
Oh, yes. The right answer is still the wrong answer. Good. You're right. It is the wrong answer, but it's the wrong answer. What went wrong? What are the units of this thing? If I'm measuring R in meters and theta in radians, this is area measured in meter radians. Is that an area? No, something went wrong. Something is missing here. We need an R. Why do we need an R?
Because the arc length is RD theta.
The arc length is RD theta. So you can think about this physically, and you can say a unit of length in that direction is RD theta. And the unit of length in this direction is R. And so we need to multiply. We have to be careful about this. We need to be thinking in terms of a length. So in Cartesian coordinates, it's easy to do it where a length is an x deviation plus a y deviation. But in polar coordinates, we have to be careful that it's an arc length plus a different part. So you can do this generally if you know all of the relationships between the x's and r's and y's and thetas. And you need to calculate something called the Jacobian matrix, which is a set of derivatives that gives you all of the key missing pieces, and from that, you take the determinant of that, which is like the degree of stretching and squeezing in that coordinate system, and that's the thing that needs to appear here. So there's a Jacobian of the coordinate transformation that needs to appear there. And I go through that in detail and how to do it in the spherical coordinate system, the Earth coordinate system, and so you can see all those little pieces. But basically, you end up with this one if you're going to polar coordinates, and if you're going to spherical or Earth coordinates, so now it's a volume integral, you end up with something that looks like r squared dr d theta d phi, and there's also a sine theta. So you get two different parts. Yes. It's a sine theta when I'm using the co-latitude that people prefer for spherical coordinates. It's a cosine of latitude. So this is the tricky part about this Earth coordinate system versus spherical. So part of what we're going to talk about more is thinking more about how to do this in interesting coordinate systems. But the reason why we need interesting coordinate systems is because some problems are better in a native coordinate system that really makes everything natural. So it's, even though it's going to seem wickedly complicated, the transformation of coordinates, and that's a big part of the work we have to do for tomorrow, it's going to be worth it because it's going to make all of our integrals much simpler. And so a lot of the homework problems are based about integrate a cylinder in this particular, integrate a cylinder, integrate a sphere, integrate a rectangle, integrate a cube. In all of those cases, it will really benefit to think, what's the simplest way I could set up the coordinate system so that all of my limits on my integrals are expressed naturally in that coordinate system. So if you don't do that, you will spend a huge amount of time trying to figure out all these crazy trig integral formulas. If you do that, it's normally like the integrals are really obvious and simple. So that's kind of the big magic for the homework and why we're spending some time talking about this. The last thing I wanted to talk about before we go is, all right, we've been doing really boring things. We've been integrating z equals 1 case. What are some other things we can put in there? What are some other things I might want to integrate over? What else might I want to know about the circle, say, other than its area? What if the circle was made out of, An object made out of something. What if the circle is made out of metal? And I know the density of the metal. What might I want to know about the circle?
It's mass.
It's mass. So how do I get mass out of a formula like that? Z would actually be my density. So I want to do a volume integral of the density. dx, dy, dz. That would give me the mass of the object. Here's the cool thing. This formula doesn't change if I make the density variable. I can make it heavier on one part than on a different part. I still get the mass. So let's suppose that it's heavy down here and light up there. This formula still works great. What else do I want to know about something that's heavy like this in one part and light in the other part?
The center of mass?
Where's the center of mass? So how do I figure out the center of mass from this? I need to integrate something like the mass times its distance. And in fact, that's exactly what you do. So the center of mass, which is the density weighted position, is the integral of the density times position, dx, dy, dz, over the integral of density. So I have a position, and I'm weighting the position by the local density. And then down here, I have just the density. And I've written this funny angle bracket to indicate average. Here I mean a density weighted average. But I could have also equally well talked about an area weighted average of x. Where I just take my density to be 1. In general, building things like this is really powerful, that I take one integral that has kind of an operational part, and then I normalize it by another integral. In fact, we didn't even say, how do you get the density? You get the density the same way. You measure the mass over the volume. It's one of these. I do the integral that gives me the mass, which is the density times the volume, and then I do the one below that's just the volume. So that would give me the density back. But I also could have done crazy things like this, which when we get to the Fourier transform, I could have said, what if I multiply something times sine up here, and that same thing, just the sine part, but not the function times sine. I could normalize an integral of a Fourier component times a function by the magnitude of that Fourier component. I could talk about all kinds of other averages. I could think about the number, the data content in a piece of software based on this kind of an arrangement by converting this into a sum over all the bits. This idea is the essence of what we mean by averaging. We take an integral and then we normalize that integral based on some measure. So averaging is an integral operation, which is part of this. So is it, all right, so last time we talked about if differentiation is a linear operation. Is integration a linear operation? It is. In fact, right at the beginning of the notes for this chapter, I show that it is by just following through from the Riemann sum definition. So averaging is a linear operation. So if we take the average of multiple things, the average of all of them is the average of the individual averages. But now, in a way that we'll talk about next time, is a tricky piece. You have to be careful about the average of ratios. All right. Cool. Oh, the answer key I just put up, and, the next homework I put up last night, actually, if anybody was paying attention. But if there are any issues with that, send me an email, because they should be up. And tonight at midnight, or 1 minute shy of midnight, you should get your review assignments automatically. So also let me know if that doesn't happen tomorrow. I think I said that right.
Yeah, but I thought it was special.
That's for like, also.
Mine was like schoolwork,
Yeah, ours is.
share.
I'm not sure.